Hi, everybody, and welcome again to, we are actually in the second week. And before you know it, we're going to be finishing the semester, at least. That's how speeds usually tend to be. Anyway, today, chapter 3. I know somebody asked a question. I forgot. I think it's in the Canvas already. Hold on. Yeah, I have the name in here. Is it on Canvas? No. Maybe I did not refresh the window. Yeah, actually, Marco asked a question about the homework. Usually, typically for the homework, when I post it, I don't know, is there any homework that you guys see it so far? Because it should not be yet. At least maybe by this weekend, you will see stuff. Anyway, the problems, usually I try to also give you specifically what problems you're going to be doing. Okay. And I know Marco is here, actually. Is that your question, Marco, or is it something else? Okay, yeah. So I'm going to give you specifically what problems you're supposed to be working on. You're not going to be working in the dark. As a matter of fact, sometimes they even post the same questions actually from the book on Canvas, so that you guys know exactly what you're doing. And then the other thing also, I encourage you strongly to work together in homework. Homework is not an exam. It's actually a learning opportunity for you guys. So if you are comfortable working with somebody, provided you work in a safe environment, meaning working together online. And if you have to meet, if you want to meet together, you observe all of the rules in terms of basically safety and things that are related to what's going on right now. So that's basically the only requirement I have for it. So it's not an exam. As a matter of fact, if you have difficulty with it, you are very much encouraged to ask. I mean, ask me. Okay, and I will be more than happy to help to make sure that the question is answered and answered correctly, or at least you know what's going on. And for the benefit of everybody else, we can post it so that everybody else can benefit from it. Usually on your day, basically, of this day is kind of busy, but we can meet maybe on Monday or on Wednesday, or even better on Friday, because Fridays I have a little bit more free time than any other time. With the exception of, I think I have a monthly meetings on Fridays. Other than that, sometimes department meetings, other than that, usually Fridays are actually very good to meet and do things like this one. So you can request at least ahead of time that I have a question of this specific problem, or this question is this specific homework, or this specific assignment or something, and I need clarifications, can we meet? And it's preferably that you tell me, first of all, in your options, then I will look into the schedule and see if it's fine. If not, I'll give you a couple of other options, and hopefully we will come up with a meeting. Now, if the meeting covers only things that are of particular interest to you, and nobody else really has any business knowing about what we're doing, then at that point, we're going to keep the discussion basically private. But most of the time, what happened in this case, your question actually will benefit everybody else. So what I will do, I will ask your permission to record the session, just like what we're doing right now, and then post it later for the benefit of everybody. If it's a question related to the homework, I mean, 99% of the time, that's a question that's going to benefit everybody else. So what I will do is I will record that session. Of course, if you choose not to record parts of it, we were going to basically not record those parts, and then post it on Canvas again so that everybody else can benefit from the discussion. If, on the other hand, the question comes through the inbox, okay, and it's again related to homework or the class benefits, then I can choose to reply to, hey, look at this question in here. It was from one of you guys, and it's a really good question, and I think it's going to benefit everybody else. This is what my thoughts are on it. Obviously, I don't claim to know it all. If I make a mistake, please correct me, okay? So that's basically the whole idea on how this works, okay? Now, if it's again related to only specifically on your working basically environment and things that are specifically related to, then in this case is going to stay basically just in the realm of what it's supposed to be. Okay, so that's in a nutshell basically in terms of communications and homework and things like that. Does this make sense to you guys? Do you think this is a acceptable approach?
Yes.
Yeah, sounds good.
Okay, very good. So today we're doing chapter 3. I mean, you will notice that this chapters are kind of light, so probably we're going to finish it quickly. And I don't think that we're going to jump in chapter 4 because, I mean, these concepts are actually a little bit, they need to sink in because we will have more stuff down the road. So we need to get these things. At some point, we will be combining chapters and I will let you know, okay? So actually, I need to move this to leave it where it was and move this one to the other screen because I have had bad experience with the pen on the other screen. Okay, so let me share with you the screen. So we're looking at chapter 3, namely the linear motion. I forgot to mention something in here. First of all, you will have assignments starting from the end of this week. And today is actually when your assignment is due. So don't forget that. Please make sure that before the end of the day, so that you're not penalized, you don't lose unnecessarily points, that you get everything in place in terms of your discussion assignment and things like that, okay? So I wanted to make sure that that's you're aware of. There is actually another thing related to the Mars landing, that the competition, not a basically challenge, not a competition, involving anybody actually, whether you're involved in the STEM Center or not, you're welcome to participate. And I think the link was sent by the STEM Center last time. If you don't have it, please let me know. And that is scheduled for March 11th, which is not too long from now, because this month is only 28 days. So in about 3 or 4 weeks time, we're going to have that challenge basically. And then we're gonna meet in a sense, we're going to meet in the, okay. Brandon, did you want the camera to be on? Okay, good. So basically, we're going to meet on the day after, which is March 12th, to basically chat about the challenge. I'm hoping that you guys also can participate because this is open for everybody. So you're welcome to participate. And if you really have any ideas or you want me to help you with what you want to do, you can let me know also. So you are very much encouraged also to participate just because the STEM Center, because actually it's my my stuff, it's not the STEM Center. So and it's open for both engineering and non-engineering students. So you're welcome to participate in that, okay? So that's related to last Thursday's landing of the Mars rover. So this chapter talks about basically motion. What you need to understand is, where is my pen? Is motion. The word motion, the way it works in here, oh man, I hate it when it does that, is velocity. When an object moves, it has velocity. When an object is not moving, it has no velocity. So usually when we talk about motion, what we mean by it is velocity. Even an object that is not in motion has a zero velocity. So it's a state basically in which objects basically tend to be in. The fact that motion, which is velocity, can change in magnitude, that is another story. The fact that it can be zero, that is another story. So the whole discussion in here is about motion, namely velocity. That is the topic of the day, okay? The concept of speed is a little bit different in a sense that it's the magnitude of the motion. Before I go into that step in here, motion is actually, in general, is relative. What that means is the following. And I think we mentioned that last time when we spoke about the Earth being a reference of a referential frame, basically where we're sitting in it and it's in motion. And we think that we are stationary, but we are not. We are moving because the Earth is moving. And I think we discussed that. The same thing is true, actually, when you're sitting in your car and the car is moving. Are you really moving yourself or are you stationary? To answer that question, you really have to tell me with respect to what? Okay. With respect to the person sitting on the outside of the car, and the car is zooming by him or her, you're actually in motion because the car is in motion. Okay, so you yourself in your reference frame probably you're not moving because you're sitting in your car. You're actually not moving. The car is moving, but not you. The person who's sitting next to you actually can see you all the time. He or she can see you now and pinpoint exactly where you are in the car. You are, for example, in the driver's seat, okay? A second later or an hour later, as long as you stay in the car together, okay? That same observer, the passenger, can still point to you and note that your position did not change. You stay in your place. So after, let's say, for example, a minute or two, that person will measure your position with respect to your car and it did not change. Therefore, you're not in motion as far as that person is concerned. You're stationary, you're not moving. And the same thing can be said about that person, unless the other person decided all of a sudden to move. I mean, probably the example of a car is a better example. Train would be more appropriate, or an airplane would be more appropriate. Because if you're sitting in the train and you're sitting, for example, in your seat and you don't move from it, you're actually not moving as far as the person sitting next to you, for example, on the other side of the aisle. But if you decide all of a sudden to move, that person will note your motion. Will say, okay, you actually have moved. Okay, a question came in, and it's basically you have to do the assignment today, okay? Otherwise, you're going to lose points unnecessarily, okay? It's very, very important you go back and make sure you do everything you're supposed to do. And of course, it's never too late. At least better get partial credit than not get any credit whatsoever. I hope that answers the question.
The assignment was the flat earth, right?
Yes, okay, the first discussion that is due today. Okay, so please take care of it as soon as possible. And there were 2 prompts in it. The first prompt was to introduce yourself with all of the things and basically come up with the resources and post them today. I mean, not today, actually, last Saturday. And also post replies to your peers by today. And now if you did not do the first part, you really have to have that part in as soon as possible, so that at least you get partial credit, then no credit whatsoever. And then also post your replies so that you have everybody you have your 2 replies, at least you get the credit for it, okay? So do it today before is it 11 p.m. today? Okay, I want to make sure that everybody is on board on this. I hope that answers the question. Okay. Anyway, what was I talking about? So basically, that's the point with the motion being relative. So you could be sitting in a train and the person next to you does not note you at all moving, albeit the train could be moving with a person sitting in the station, for example, waiting for you guys to arrive. That person will note your position changing over time. As far as he's concerned, the train was here and then it was here and maybe you did not move. So that's what we mean by motion is relative. Depends basically on the observer, depends on the person who's actually doing the measurement, okay? Where that person is sitting. So that's really what that means, okay? And then again, the concept of speed is when what we mean by the magnitude of the velocity, that's all. Basically, how big it is. So when a person tells you I'm doing 50 miles per hour, what they are talking about in this case is the speed. But if they tell you I'm going east on 91, then you know which direction that person is going. 91 is probably north-south, isn't it? So maybe north, okay? So you know which direction that person is moving. Let's give a better example. Highway 60, for example, is a better example. So if that person is going east on 60, you know not only the magnitude, but also the direction with which that person is moving. That is the concept of velocity. So velocity is a vector. Okay. Then we're going to discuss the free fall, which is really falling at a given. Before that, we're going to discuss the acceleration, which Mr. Galileo actually has introduced to us and enabled us to quantify the motion in general better than before. Okay, and then we're going to consider the acceleration in the presence of the Earth, basically on the Earth, if there is no other acceleration other than that of gravity. Okay, if your acceleration happened to be that of a gravity, you are in free fall. Okay. And at the end, we're going to be adding vectors in here. This is important because I think there is an assignment related to it and how to add velocities. So you really need to know that a little bit, okay? It's not going to be complicated geometry, but it's hope that you should be able to get the numbers correctly so that at least you get the direction of how the velocities is. Namely, here's a scenario. You are on a river. Oops, how come I jumped all the way to the second slide? Okay, you are on there is a river, and the river is flowing this way, for example, at a steady rate. It doesn't matter what that rate is, but it's flowing in this direction. And you are here, and you would want to end up in this location. Are you going to straight swim this way? Because if you do, here is the trouble. Your velocity will take you, at least in your mind, in your calculation, this way. But because the river is drifting this way, you'll find yourself in this point. You're not going to find yourself in here. So what you do in here, you pull up your calculator and you decide on which direction I can swim. If I swim in this way and the river is actually flowing this way, I will end up where I'm supposed to be, okay? So that is in a nutshell basically what the last point is, okay? So this is really what we mean by it. This point, I think we talked about it last time. The fact that we are sitting in a reference frame that is spinning. First of all, the Earth is rotating on its axis. So that is one motion. And we are sitting not in its center of rotation. We are sitting far away from its center of rotation by an amount which is 6,400 kilometers, 6,000, almost 6,500 kilometers from the center of the Earth. So that's the radius of the Earth, okay? So that is in one motion. That is 24 hours. In addition to that, the Earth is actually going around the sun once a year. So actually we're moving around the sun. And I think we estimated last time its velocity to being around 100,000 kilometers per hour. That's a lot of velocity. That's a huge velocity, 60,000 miles per hour. So that's basically in a nutshell the speed with which we're moving in this frame. Albeit we think that we're stationary, we're sitting. I mean, we have my pen in here, I have my mouse next to me, I have my everything in here. But if you're thinking about it that way, because I am in a reference frame, for example, with respect to at least to another origin in here, I am relatively speaking stationary. But with respect to the sun, I am actually moving around it with tremendous speed. As a matter of fact, the sun dragging with it the Earth, which is dragging us with it, we're moving around the center of the galaxy too. So the entire thing is going around, what is it? What is that? Sagittarius, the star. Sagittarius, a star, where the black hole is, and that's where the center of the galaxy is, and that's where that's actually motion of the entire thing. So if you think that the sun is stationary, that's also not true, because the sun is actually going around the galaxy at tremendous speeds too. I mean, the radius is tremendous. It's about what, 30,000 light years? And it takes us about almost 250 million years or a little more to go once around the axis of the sun, around the, the axis of the galaxy. But it's a motion nonetheless, which is huge, actually, with tremendous speeds too. And if you think that's not enough, the galaxy itself is in motion too. And the entire local group is motion. So everything is moving, nothing is stationary. So when I say that this object is stationary, is with respect to some origin, with respect to some reference frame, with respect to some point in space, okay? So that's what we mean by motion being relative. Motion, or the speed, is a rate of something with respect to something, and it's the rate at which distance is covered with respect to time. Okay. Example in here, a girl runs 4 meters in 2 seconds. Her speed then is 4 divided by 2, which is 2 meters for every second, provided that she's running at constant speed. If she's running at constant speed, and we know that she covers 4 meters for 2 seconds, that means in 1 second, she covers 2 meters. Because here is the scenario in this example. So we have the distance, which is 4 meters. That's 1, 2, and 3, and 4 meters. This, I know, the whole trip is actually 2 seconds. So she must have covered this half the distance, which is 2 meters, by the way, in 1 second. And the other half in the other second, for a total of 2 seconds to cover the 4 meters. So her speed then is this 2 meters in 1 second. You ask me, how long does it take her to cover 1 meter only? 1 meter is this much, and she's going to cover it in half this time, because 1 meter is half the 2 meters in here. Okay, so this is a 2 seconds, by the way, and this, each one of this is 1 meter. So in this case, in 1 meter will be covered in half a second, and it's all of it the same thing. So it's a rate. The key word in here is rate. And the units for it is, in SI, is meter per second. In the Système International, it's always meter per second, because distances are measured in meters, time is measured in second. In our daily experience, we use miles per hour. That's what we use in daily experience. We say something is going 50 miles per hour, something is going 60 miles per hour, something is going 120 miles per hour. Okay? So that's our daily experience. Is 2 meters per second a lot or a less? Is it faster than a car or slower than a car? What do you guys think?
Slower.
By how much? That's the key. Is it a lot slower or just barely slower? That's the key thing in here.
It's slower than idle.
Okay, let's see here how we can do this conversion, because converting sometimes is tricky. We know that there are 1,000 meters for each kilometer. The K in kilometer stands for 1,000. Okay, and a kilometer, or at least 1.6 kilometers, 1.60 something, is a mile. That's one thing. We know also there are 60 minutes in 1 hour, and there is 60 seconds in a minute. So there are 3,600, which is 60 times 60 seconds in an hour. I know how many meters per second. That's 2 meters, sorry, 2 meters per second. And a meter is 1,000th of a kilometer. That's what a meter is. And the second is, what is it, 3,600. Or 3,600 second is an hour, okay? So I can put in here and do the conversions and convert this one, and it's gonna be what? Times 3.6 at the end. That's gonna be in kilometers per hour. So if I do this one, cancel the, not 36,000, 3,600, I'm sorry, I probably have put an extra zero in there. Anyway, it's going to be about 7.2 kilometers per hour, okay? 7.2 kilometers per hour is roughly about 5 miles per hour, okay? So it's not bad, you're right. So it's not bad. Because 5 miles per hour tells you something. 2 meters per second doesn't tell you much. 20 meters per second is a lot of speed. That's about what, 50 miles. I'm not sure about my conversion. Is my conversion correct? I think it is, okay? So when you're doing 20 meters per second, it's a lot of, it's 50 miles per hour, okay? So that's roughly about this conversion, okay? If you're doing 40 meters per second, that's twice as much. So it's not 50, it's about 100 miles. So if the police officer stops you and he tell you that you're doing 100 miles per hour, you can always argue with him or her and tell him, look, I'm actually doing only 40. You got me a ticket for 100 miles per hour, but I'm doing 40. Show them this math, it's 40 meters per second. Okay? Do you think he's gonna adjust, or they're going to adjust the ticket for you?
Nope.
Well, the sign, because he will tell you that the speed limit in here, it's 65, and you are doing 100. Tell them you're wrong. It's 65, and I'm doing only 40. Okay? Don't plug in the units though. Okay, because if you plug in the units, you're in trouble. That's a good defense. Try it. You might win some cases. Okay? Don't mention my name, please, because I will not support you on this thing in here. Okay? You're on your own. Don't speed, okay? That doesn't mean that this is something that you should go and test it, okay? Because it's very dangerous. Anyway, so again, the key thing to take from here is this rate, distance over time. Forget about this conversion. This is just for the peace of mind, because sometimes some of these problems, they will have numbers in them, and numbers don't tell you much unless you put them in the units that you're familiar with, okay? You're familiar with the miles per hour, so if you want to, you can convert it this way and know what 2 meters per second is. 5 miles per hour, that is actually a good run, decent run. A person running 5 miles per hour, that is actually a decent jog, okay? So that's a number that you probably can go with. But a car moving at 2 meters per second, that is actually very slow. As you can see, it's 5 miles per hour. It's way below any speed limit that we can do, okay? So that's basically what, because numbers tell you something. They speak to you. They tell you what's going on, okay? Since you're familiar with the miles per hour, that's the purpose of this exercise. The point in here is that the speed is a rate of something over something. It's the ratio of how much distance covered versus the time that it covers in it, the lapse in time during that event, okay? The average speed is the distance covered divided by the total travel time. Doesn't indicate various instantaneous speeds. So there is something that you have to understand in there, instantaneous versus an average. Let's say, for example, you leave home at 8 o'clock in the morning, go to work or school, okay? Stay there for about 4 or 5 hours, 10 hours, whatever your shift is supposed to be, school or work, and then come back home. Now, the minute you step back home, how much distance did you cover? What is your displacement?
0.
You left home and you came back home. Your starting point is your ending point. What is your displacement in this case?
Is it just 0? 0.
Yeah, it should be. Yep. So in this case, the average speed is 0. But you have to take into account when did you calculate it. Okay, that's all. The average speed is kind of tricky way a little bit. But usually, if I'm interested in the distance, I can say, okay, it's actually this sum of the two divided by the time. But you spent hours sitting on your desk. At that time, your instantaneous speed was 0 miles per hour or 0 meters per second. Okay. And in here, you probably went with the speed limit. Let's say, for example, you're on the freeway, 65 miles per hour. And you stayed in there. So if you just consider this distance, let's say, for example, it's 10 miles, the distance from work to home. So you moved 10 miles at 65 miles per hour. So you can calculate it took you what, probably 10, 15 minutes to get there. Then by the time you came to your place at work, you're sitting still. So your average speed at that point is 0 miles per hour. But if the whole thing from home to here, after the shift is over, at that point, let's say, for example, it's 10 hours, that still counts as part of your average. 0 plus 65 divided by the entire time in this case. So if the distance is 10 miles and it took you 10 hours of shift, your actual speed on this case on average is 10 over 10, which is 1 mile per hour, okay? So that's basically the concept of the average in this case. Average is usually over a long span of time, which can be usually tend to be a smaller number than the instantaneous speed. The instantaneous speed, the minute you look at your speedometer, that is actually giving you the instantaneous speed, the speed at that moment. The average speed of driving 30 kilometers in 1 hour is the same as the average speed of driving what over what? 30 kilometers in half an hour? No, it's not the same. 30 kilometers in half an hour, that means in 1 hour, I do another 30 kilometers, that's 60 kilometers in 1 hour. 30 kilometers in 2 hours? No, that means in every hour I did 30, I did 15, because in 1 hour I do 15, in another hour I do 15, that's 15 kilometers per hour. 60 kilometers in half an hour, that's not correct either. That means in the first half hour, I do 60 kilometers. In the next half hour, I do another 60 kilometers. That means the average speed in here is 120 kilometers per hour. 60 kilometers in 2 hours is a correct answer because That means in the first hour I did 30 kilometers, in the second hour I did 30 kilometers for a total of 60 kilometers in 2 hours. And that is the same thing as 30 kilometers in 1 hour. I mean, all you have to do is just do the fractions and you're going to get the correct answer. So 30 divided by 1/2, when I divide by fraction, I multiply by its reciprocal. This is clearly equal to 60. Plug it in your calculator, you're going to find 60. This one, on the other hand, is 30 divided by 2. That is 15. That is not the same as this number. This one, on the other hand, 60 divided by 1/2. Again, that is, if I plug it in the calculator, it's going to be 120, because when you divide by fraction, you multiply by its reciprocal. So it's 60 times 2, which is 120. The final one in here is 60 divided by 2, and that is equal to 30. 60 divided by 2 is 30 kilometers per hour, which is exactly what the speed is. So the correct answer is D. You are expected to do this kind of algebra. This is not something that is out of the realm of the possibility that you should have difficulty with it. Dividing two numbers in here, you need to have access to a basic calculator in here if you have difficulty with these things. Okay. Does everybody understand what the rationale behind this thing?
Yeah.
Okay. So this is basically the idea. Again, the instantaneous speed, this is as opposed to average velocity or average speed, because this speed is in that moment. In other words, you're going to do two experiments, one after the other, immediately. So what you do in this case, you find the first position and you find the second position, and you take the difference between the two, that is the distance traveled, and you take this time. You look at the clock when you looked at this measurement of the position, and you look at the second clock in here when you measure the second position, and then you find the difference between the two times, and that is the lapse of time that took to go from first position to the second position, and you divide this ratio of the final position minus the initial position over the final time minus the initial time, when these two times are close from one another, very close from one another. This is what we call instantaneous velocity, the velocity at that moment. If the time span is very long, then in this case, you're talking about an average velocity, because the object would have taken probably a lot of things to go before you're there. So you're not asking me how close it's going to get, as close as you can get. How close should I make the second measurement? As close as you can get, okay? For those who are math-minded people, this is actually where calculus comes into play, okay? If you don't care about calculus, make sure that you look at the watch and then look at it again immediately. Don't wait too long, because if you waited too long, probably waited too much, and then you're not dealing with the instantaneous velocity. So if you look at the speedometer, what the speedometer has done for you is this measurement. Took two different instances that's very close from one another and gave you the distance the wheels has spun, and that's going to give you the instantaneous velocity, the velocity at the moment. If you look again, probably the car has changed speed already, so the instantaneous velocity has changed. Obviously, if you're traveling in a car, the speed will go up and down, so on average, you have a value. And that is the time it takes you to go from one place to the other, okay? If you use one of those navigation software like Waze or Google Maps or anything like that, and they give you the ETA, the estimated time of arrival, then actually what they're basing it off of, they're basing it off of an average speed, not on the instantaneous speed. So at that moment, probably you're going 70 miles per hour, but you're wondering, hey, the distance is only 40 miles. I should make it in less than half an hour, or probably about half an hour. But then you look at it, it's giving you more than that. It gives you almost 50 minutes or so, because that software already has averaged the traffic on from your location to where you're supposed to be, and gave you the estimated time of arrival based on the distance and the average velocity, okay? So this is something that is good to know. So again, I mentioned the fact that the velocity is a vector, and because it has the direction and magnitude. So the velocity can change in one of two ways. For example, going from 50 miles per hour up to, let's say, for example, 50 miles per hour. In this case, you have changed velocity. Even if you kept the direction, even if you kept moving in the same direction. The other way also of changing the velocity, if you're going from 50 miles per hour and you kept your 50 miles per hour, you didn't change it. So the speed did not change, but the direction changes. So initially you were going this way and now you're going this way. So it's clearly you have changed direction. So that too, the velocity has changed, okay? In general, it's both magnitude and direction. So both of them can potentially change, and they do, okay? So that's how you change velocity. You change velocity by changing either its direction or its magnitude or both. So constant speed is steady speed, neither speeding nor slowing down. Constant velocity has to have two things, constant speed and constant direction. So to go back into my original example, this too is constant speed. Going on a curve is constant speed, but it's not constant velocity because the velocity has changed direction in this case. Therefore, it's not constant velocity, albeit you still have your cruise control on. And this is, again, repetition of what we've been talking. The acceleration is the rate of change of velocity with respect to time. Okay, so basically, in magnitude, the acceleration is the change in speed over time. That's one way of doing it. The other way also, at least on an incline, okay? The other way of doing it is actually how much it changes when you are on a curve. And the magnitude for that is a little bit complicated, but we'll get to it at some point in the future. It's going to be the square of the velocity divided by the radius of the curvature. So we're going to get to it later on. But both of them will give you an acceleration. This is called the linear acceleration because you're accelerating in a line. You're changing your speed. You were doing 50 miles, and now you're doing 55 miles per hour. Okay, so definitely you have changed the speed in this case, but in a linear fashion. The other one, the one that is actually going on a curve, is sometimes called centripetal acceleration, sometimes called normal acceleration, and that is because it's perpendicular to the path of the that you're taking, and the magnitude may stay the same. So the speed can stay 50 miles per hour, but the direction is changing. Okay. So we'll get into more details about this value later on when we get it, okay? But what you need to know now is how the velocity changes with time. That is the acceleration. So that was due to Mr. Galileo, okay? Here is the case in here. So acceleration changes in speed or changes in direction or both in general, okay? Case in point, the car making a turn, that is actually an acceleration too, because it's turning, it's changing its direction. The velocity, change in velocity. So in general, this is the formula that you go by. As I said before, this is really applicable only to the type of linear acceleration, such as this case in here, for example. Your car speed is presently 40 kilometers per hour. Your car speed 5 seconds later is 45 miles per hour, 45 kilometers per hour. So it has gained 5 kilometers in this 5 seconds. So your acceleration in this case is the speed gained, which is 5 kilometers per hour in 5 seconds. So when you divide the ratio, you're going to find it gain 1 kilometer per hour for every second. So that is your acceleration, okay? Obviously, the car has accelerated in this situation. If you have decelerated, if you were doing 50 miles per hour and you dropped the speed, 40 kilometers per hour, I'm sorry, and you drop speed to 35 kilometers per hour, then in this case, this number will be negative, that's all. You have 35 minus 40, which is -5, and you divide it again by 5, is going to be -1 kilometers per hour per second, meaning you actually have decelerated. You're losing speed in that situation, okay? An automobile, in general, we call it acceleration, even if it's negative, okay? This value is algebraic. This value can be positive or negative. In daily talk, we say acceleration, really meaning with it gaining speed. and deceleration is losing speed, but it doesn't matter. Both of them, you can call them acceleration. If it's positive, that means you actually, the speed is increasing. If it's negative, that means the speed is decreasing. End of the story. So that's basically in a nutshell. So an automobile is accelerating when it is A, slowing down to a stop. That is correct. B, rounding a curve at steady speed. That is correct. And C, both of the above, and that is correct. D, neither of the above. Now, that is not correct because A is true and B is true. Now, I'm going to ask you to think about this point because this is very important, and sometimes this is where you guys lose points, okay? If I have this question on Canvas in one of the quizzes or the exam or something like that, and the question came up like this, asks you to tell me if the car is so-and-so, and you, when you read the question, you see the first time in here and say, oh, slowing down to a stop. Yeah, it has accelerated, it has lost velocity, its magnitude has changed. So the correct answer is A. And you move on. Canvas will give you 0 credit for the answer. The reason being because Canvas knows the correct answer is being C in this case. Albeit you're right. I mean, the car has accelerated when you chose A. If on the other hand, you read through and you thought, yo, no, B also rounding a curve at a steady speed, that too is correct. But you cannot circle both. Now you're confused. Did he really mean by accelerated gaining speed only? And this is probably losing speed, so maybe it's not accelerated. I just said it's an algebraic value, so it doesn't matter if you gain speed or you lose speed, that's accelerated. So I know for a fact that A is correct. But if you're confused and you say, no, I think it's B, you are actually correct too, in a sense that B is also correct answer too. But Canvas still will give you an incorrect 0 basically in this question, doesn't give you any credit whatsoever because it knows the answer is C, which is the first item in here. When you're taking quizzes or exams or things like that, please read the question from top to bottom. You may have other options than what is above, what you have seen so far. So that is the point that I want you to guys think about for this chapter. When taking exams, you're supposed to read the question thoroughly and make sure your answer is clear and not ambiguous, okay? Albeit now you have A, which is potentially correct, B, which is potentially correct, not potentially, they're both correct 100%, but the question here is asking for C, not A or B, okay? Now, if you think after the exam that, hey, I think I should have partial credit for this question, you may or may not have partial credit, you let me know. So if I come back to this question and I agree with you that, you know what, I think you deserve partial credit for this question because you were not wrong, I can opt to give you partial credit for that question and override basically what Canvas has done for you. Does this make sense to you guys?
Yeah.
Yeah, it makes sense.
Yes.
It makes
Yeah,
sense.
that makes sense.
From now on, this is item 1 of the discussion, so please focus on it, okay? Make sure that you have an understanding of what is asked from you and you're not losing unnecessary points, that you know the question, basically the answer to the question. Here is a question that hopefully there is no confusion about it. Acceleration and velocities are actually the same. That is nonsense. They are not the same. As a matter of fact, the units for one are completely different than the units for the other. One of them is in meter per second, and the other one is a meter per second per second. They're completely different entities, okay? As a matter of fact, one of them can be positive and the other one can be negative. You could be traveling, let's say, for example, at 50 meters per second, okay, in one way, and in the same time losing speed at the rate of 1 meter per second per second. So if you ask me what's your speed next time around, if you move a little after 1 second, actually it's going to drop from 50 down to 49 meters per second. Because for every second you're losing that much speed. So in this case, the magnitudes are different, the units are different, and the directions are different. So is A an option? They are not.
No.
They are not the same. Different units, different rates, but for different quantities. That sounds more like it. C, the same when direction is not a factor. That's nonsense, okay? The same when an object is free falling. Absolutely not, okay? So Correct answer is B. Again, Mr. Galileo did a lot of experiments with the incline, okay? And he was able actually to find the value of G that we use nowadays for the experiments. This is the gravity on Earth, okay? Which is approximately 10 meters per second for each second. All he did was, based on the inclination, he was able to find it, and then as he increases the inclination, the acceleration started to grow and more and more and more. When the object is actually at 90 degrees, the object is actually free falling. In other words, the distance between the first and the second, and the distance between the second and the third, and the distance between the third and the fourth, and the fourth and the fifth, and the fifth and the second is increasing at higher and higher rates because of there is a relationship that we're going to discover very shortly, namely the distance traveled is 1/2 times the acceleration times the time squared. So that turns out to be the expression that is going to govern this whole displacement in here. But the velocity is changing at that rate, which is g times t. So every second, it's that many g's, which is 10 meters per second, times that second. So if your speed, if you drop an object from a height, doesn't matter how high it is, and you wait 1 second, what is its speed after 1 second? It was at rest when you drop it. Now after 1 second, it's going to be exactly 10 meters per second. So if it started from rest, if it started moving already, you add 10 meters per second to it, to its original motion. Now, if you wait another second, you add another 10 meters per second to the initial speed. So it's going to move faster and faster, 20 meters per second. If you wait another third second, it's going to travel even faster, 30 meters per second. Hence, this distance is being higher and higher and higher because it's going to be moving faster and faster and faster for every span of seconds down the road. So the distance covered is going to be more and more and more and more down the road. Okay, so that is basically what the experiment is all about, and that is what we call a free fall. So when an object is free falling, that means its acceleration is g. There is no air resistance. Okay. And free-falling objects on Earth accelerate at the rate of 10 meters per second. I wrote it 10 meters per second squared because second times second is second squared. That is how we write it usually, which is roughly about 10 meters per second. To be specific, it's actually more like 9.8. That's how much the acceleration on Earth is. That's how he found it, okay? So again, this is the expression that I wrote earlier. I wrote it symbolically, but it's the same thing in here. The velocity is the acceleration times time, and the acceleration is 10 on Earth. So if you are curious trying to find the speeds, and this graph is for this is for the distance probably, the speed will increase, as I said before, if you drop it from rest. The first second by 10 meters per second to 0, so it's going to be 10 meters per second. The second, you add another 10 meters per second to an already existing 10 meters per second for a total of 20 meters per second. The third second, you add another 10 meters per second to an already existing 20 meters per second for a total of 30 seconds. So you can guess what's going to happen after the fourth second. On the fourth second is going to be
40.
Okay, that is item 2 of the discussion. So you're going to predict what happened on the fourth second, okay? And the correct answer is obviously 40 meters per second. That is the speed. Good, everybody?
Yeah.
Yeah.
Okay. So at a particular instant, a free-falling object has a speed of 30 meters per second. Exactly 1 second later, its speed is, so we know right now it's 30 meters per second. 1 second later. So it doesn't mean that it could have started already with 30 meters per second. So is it going to stay the same?
No.
It's going to increase by a factor of 10. As a matter of fact, it's going to be 40 meters per second. Is it the same? That is not correct. Is it 35 meters per second? Absolutely not correct.
More than 35.
60 meters per second? Sorry?
It was more than 35.
Yeah, it's actually we know exactly how much it's going to be. It's going to be 40 meters per second, okay? Because it's free falling, that means there is no friction. So we know exactly that it's moving with 10 meters per second per second. Okay. So that is the correct answer. So that is basically in a nutshell the explanation for it. This is the other expression I wrote, d equal to 1/2 of g times time squared. This is how you can, I wrote it symbolically, but it's the same thing. Now, under free acceleration, an object starts from an origin, for example. How much distance would it cover after 1 second? After 1 second, it's going to cover 1/2 times 10 times 1 squared, according to that formula. 1/2 times 10, that's 5 times 1 squared, which is 1. So it's going to be 5 meters. Okay. So it's going to cover 5 meters after 1 second. After 2 seconds, it's going to cover 1/2 times 10 times 2 squared. 1/2 times 10, that's 5. 2 squared, that's 5. 2 squared, that's 4. 4 times 5, that's 20 meters. You guys see that? That this is 4 actually. 2 squared is 4. 4 times 10, that's 40 divided by 2 is 20. After 3 seconds, it's going to be 1/2. I'm doing this now. After 3 seconds, 1/2 times 10 times 3 squared. 3 squared, if you plug it in the calculator, is 9. 9 times 10 is 90. Divided by 2 is 45 meters. See how much the distance is? It's not uniform like before as far as the velocity. And the first second, 5 meters. The second is 20 meters. The third second is 45 meters. So these distances are increasing at a higher and higher rate because of this acceleration. Because the object is not moving with constant speed. It's speeding up as it's falling. That's why it's covering more and more distances. The first discussion point was how to take the question, basically how to answer the questions, the exam. Does this make sense to you, Jason? Okay, very good. So what is this distance after falling 4 seconds for a freely falling object starting from rest? Now, after 4 seconds, we're going to do the same math in here. After 4 seconds, we have 1/2 times g, which is constant, always 10, times 4 squared. 4 squared is 16. 16 times 10 is 160, divided by 2 is 80. So the correct answer is D. Okay. Does this make sense to you guys? Yes.
Yeah.
Explain that again.
For the 80 meter, for the 4 squared is 16. I'm talking about, this is the question in here. It asks about 4 seconds. So we're going to plug in the formula. Remember, the formula I'm using in here is here. So I'm using 1/2 times 10. This number is always 10 on Earth, times the time squared. The time now is 4 seconds. So I'm going to plug in 4 in here. When I square it, it's going to be 16. That's after I square 4. This is 10, as I just said. 16 times 10, that's 160. Divided by 2 is 80. So the correct answer for this part in here is 80. Does this make sense?
Yes.
Kimberly? Okay, very good. Or whoever asked the question, I'm sorry. So how about 5 seconds? I know it's not asked in there, but let's do it for the fun of it, okay? 1/2 times 10 times 5 squared. 5 squared is 25. Times 100 times 10, that's 250. 250 divided by 2, if you plug it in the calculator, is 125 meters, and so on and so forth. So we should be able to get any answer you want, okay? If we have access to a calculator, we can do any number. So we can see that the first distance was 5 meters. The second distance was 20 meters. The third distance was 45 meters. The third one is way below the screen in here. It's at 80 meters. And the fifth one was completely outside of the scope of this thing. You see it, even if I start in here, I'm going to run out of room very quickly. So this is my 5 meters. This is my 20 meters. This is twice as much. So this is 45 meters. This is twice as much. This is about 80 meters. And this is add to it this much. It's 125 meters. And the sixth one is going to be 6 squared. That's 36 when you multiply it by 360. So it's going to be 180 and so on and so forth. Okay. So that's basically the formula that we use in this case. So the correct answer is 80 meters as we predicted. Okay. Again, I was making a big fuss over this one earlier about how the swimmer will cut and go from one place to the other. And that is explained in here also with this plane drifting. Let's say, for example, you're supposed to deliver mail with the plane in the remote areas, and there is a wind blowing. So the 60 kilometers cross, look at these words in here. You have to really be paying attention to the verbiage in here. Sometimes it's kind of confusing a little bit. You have the 60 kilometer per hour crosswind blows the 80 kilometers airplane off course at 100 kilometer per hour. So if the wind is blowing 60 kilometers per hour, and the plane is actually going 80 kilometers per hour, the plane will drift here at 100 kilometers per hour. Okay. So in this case, the angle is clearly more than 45 degrees. But that's not the question they are asking. They're not asking about this specific one, because this is a low breeze wind, so that's not blowing as hard. So it's helping the plane actually move forward, but it's moving in the wrong direction, that's all. It's supposed to go north, for example, it's going a little bit to the east. Okay, so this is more than 45, not exactly 45, if this is the situation. Now, they said if the crosswind were 80 kilometers per hour. So now here is a question. So the plane is going 80 kilometers per hour, and the wind is blowing 80 kilometers per hour. They say now the airplane would travel 113 kind of at an angle. That angle must be 45 degrees. Because if I look at this triangle in here, this is 100, this is 80, and this is 80. That is actually a right angle triangle. What is it? Is it isosceles? No. Let's see. Yeah. So the two sides are the same. Therefore, this angle, this is a 90-degree angle, by the way, because it's a right angle triangle. So this is 45, and this is 45 degrees. If you're not convinced, then you know I have access to a trig calculator. You do just the arctangent of 80 over 80, which is the arctangent of 1, which is exactly 45 degrees. So correct answer in here is 45 degrees. It's easy, because if you're pulling on your this object with 80 on this side, and the other side is you're pulling on it with the same thing, 80, so it cannot go one way or the other. It's going to go right in the middle, smack in the middle, which is 45 degrees. Not at 0 degrees, not at 9 degrees, but right smack in the middle. And that's exactly why the correct answer is 45 degrees. Okay. Does this make sense to you guys? The question? It's the second part that is actually the question. The first part is not. The first part you're taking from it just the fact that the airplane is going 80 kilometers per hour north. Okay. Now the wind is blowing 80 kilometers per hour on it east, so now it's going to go. Let me try to change cameras quickly to see if I can get. And I have to remove the background. Okay, so what is my black pen? Okay, so here is the situation. You have, this is 80 kilometers per hour. And this one also is 80 kilometers per hour. They are identical. So it cannot go this way. It cannot go that way. And because both of them are pulling with the same strength, so it's going to go straight right in the middle. Okay. And that number, if I use the Pythagorean theorem, is actually, do you guys are familiar with the Pythagorean theorem? This is the adjacent, this is the opposite, and this is the hypotenuse.
Yes.
So in this case, it's going to be 80 squared plus 80 squared under the square root. And let me check exactly how much that is, because they say that it's 100. Okay. 80 squared square root of 80 squared plus 80 squared, or 2 times 80 squared. Oh, I'm sorry, they said it's 113, didn't they? Because I found 113 in here. And yeah, it's going at 113. And the calculator proves that too. So that's basically, in a nutshell, what this question is, okay? Using the Pythagorean theorem. So this angle must be 45 degrees, okay? Does this make more sense now?
It does.
Okay, so this is basically, you're not going to get complicated situations with geometries like this one. 60 and 80 is a little bit hard, okay? 60 and 80, you can do the same idea in here. It's going to be using the Pythagorean theorem. It's going to be 60 squared plus 80 squared. And you have to have access to a calculator that does the square root if you really are given that. Most of the time, I don't think you do. But if you do, let me know, especially if you have difficulty with it. So it's going to be 60 squared plus 80 squared. This is the one where they said that it's 100, okay? It's exactly 100 according to my calculator, okay? So they are right in this case, okay? So if the wind was blowing 60 kilometers crosswind and the plane was traveling at 80 kilometers per hour, and the plane is going to go off course by at 100 miles per hour. So this is 60, this is 80. Obviously, if I add this 2, the plane is drifting closer to the 80 rather than the 60. So it's going to get at an angle much higher than 45 degrees, okay? If you're curious trying to find that angle, it should not be hard to find, which is basically using trig functions, and you should be able to find what that angle is. The bottom line is it's going to run closer because this is 80, this is 60, so it's going to run closer to the 80. Whereas in this situation, both of them are the same, so it's going to go smack in the middle, which is 45 degrees. Good? Makes sense? Not to everybody else, or not just Brandon?
It's good. Yeah. Makes sense.
Okay, very good.
Yes.
So, okay. You run at 4 meters per second in a vertical falling rain that falls at 4 meters per second. Relative to you, the raindrops are falling at an angle. So basically, I was going to draw, and I know I just removed it. So you're running at 4 meters per second, and the rain is coming to you at 4 meters per second. Falling down at 4 meters per second. So the rain is going to come at an angle of what? It's similar to the first case.
$45.
Yeah, it's going to be exactly 45. So it's going to be coming at that angle in there, okay? Have you ever driven, if you ever driven in the snow, you will see, or yeah, the snow is easier to see better than the rain, actually. You will see the flakes of the snow coming at you because you're driving probably at, hopefully not too fast. Let's say, for example, 50 miles per hour, and the snow is actually barely falling and drifting toward the ground. So it looks like to you is up falling towards the windshield, whereas it's actually still falling down. So if you're stopped and looking at it, it's actually coming down, not coming to your windshield. So it's the same factor, but that's actually the velocities are not the same. In this case, they are the same, so it's coming at you at 45 degrees, okay? Okay, watch Canvas for more assignments and things like that related to this chapter. And as I was saying earlier, I'm going to make some adjustment for some of these chapters. And you guys have any question for me before I stop the recording? If no, please finish the assignment today. It's very, very important, okay?
For the quizzes, is it like multiple choice questions?
Depending, okay, sometimes multiple choice, sometimes you actually have to work out stuff and answer them in there, okay?
Okay.
Okay, thank you.